So everybody knows that the preterm lung is an underdeveloped lung. So lung development is a complex process and is supposed to start very early during the pregnancy and also last later on in postnatal age after 3, 4, maybe 6 years of age, as you may see on the graph. So I'm now trying to explain what is really happening in the... So the lung developing as a crucial point when the alveolarization is starting. Alveolarization is the process producing the alveoli, so the basic units that are supposed to be responsible for the gas exchange. Alveoli start to be present at 24, 26 weeks with some sort of variation according to the different babies. And it's at that time that surfactant is start to be produced. Sometimes a little bit later, at around 28, again with some sort of variation. So surfactant, I will talk to you about that, will be very important to keep the alveoli open. So even if this process is very complex, as you may see from the graph, now we have a powerful tool to see that on the real life. And that tool is fetal MRI. So I'm going to show you 2 pictures of fetal MRI from a 24 and a 28 weeker. And you may see that in the 24 weeker, the lung is much smaller as compared to the 28. And there the lung is much filled of liquids, of amniotic fluid, just because there will be many more alveoli, and so much more surfactant, and so much more surface available for gas exchange. So let's enter into the details. Here you may see a normal alveolus with some sort of surfactant film in it, and especially the type 2 pneumocyte, which is supposed to be the cell producing surfactant. So let's get into the details of surfactant production. Surfactant is produced by the type 2 pneumocytes. So they start to put together all the phospholipids and some proteins, and they do that through the different cell organs, and they create some sort of very small body, which are named lamellar bodies. So these lamellar bodies that you may see in this other picture at the phospholipids, and they are, once they are created, they are approaching the cell membrane. And over there, they are just secreted into the alveolar space. So you can just understand that the number of lamellar bodies is something that will tell you something about the amount of available surfactant. Once secreted into the alveolar space, the lamellar bodies are opened up with the squeezing of alveoli, with the respiration, and they are creating this film. For the creation of surfactant film, there is a protein, surfactant protein B, that is very, very important, and I will tell you later on about that. So, why surfactant is secreted into the alveoli? Because it's there that is supposed to have its main biophysical activity. So, you know, the alveoli is something that is supposed to have force, which is called surface tension, that is acting towards the closing of the alveoli. It's a force directly just behind the center of the alveoli. So surfactant is over there creating such a film, trying to reduce surface tension, as you may see in this animation, and to keep just the surface tension. So in practical field, you may see the difference between a diseased alveoli and a normal one. In this RDS, it's pretty open, it's big, and there is a lot of air in it. The diseased alveoli, it's unfortunately very small, with not so much air in it, and it's very stiff, just because the surface tension is closing it, and there is not enough surfactant to face the surface tension. So we now have many tools to see that in the real life. One of these is lung ultrasound, and you may see here the difference because a normal alveolus and a diseased one, because I'm going to show you that's a normal lung with no RDS, with some sort of vertical lines, but quite enough hair in it. And on the other side, there is an RDS lung, which is totally white, which means no air in it, and totally stiff and closed alveoli. A few years ago, there was a very nice meta-analysis in the British Medical Journal, meta-analyzing all the data about CPAP and surfactant, demonstrating that the early CPAP policy followed by selective surfactant administration is reducing BPD and or mortality. If you look at these images here, you may see 2 babies. This one is a nice baby under CPAP, and you may see his lung pretty pink, pretty opened with just a small volume excursion. The other one is a baby intubated under invasive mechanical ventilation. You see the lungs are pretty red, they got inflamed, they are stiff, and they are subjected to a quite relevant excursion in terms of volume. If we go into these lungs and we see that in details, you may see what is happening. The lungs are really opened up and then collapsed in a cyclic way under mechanical ventilation. And this is what is giving them inflammation as compared to the CPAP lung that are pretty nice and very well ventilated. So someone had the opportunity to study that with some video under lung microscopy in pigs. Clearly, we cannot do that in babies. And you may see exactly what I'm talking about in this. From a mechanical point of view, when we are talking about CPAP and mechanical ventilation, are they really different? Yes, indeed, because if you look at these graphs over here, you may see how CPAP and mechanical ventilation are different in terms of volumes and in terms of pressure. So the excursion in pressure or in volume under CPAP is smaller as compared to those in mechanical ventilation. There are bigger volumes, bigger pressures. As I told you, this is what is giving you inflammation. So unfortunately, some years ago, there was a baby dying for a car accident, and this baby was a BPD baby. So researchers had the opportunity to have a lung histology from this baby to actually verify what was happening into his lung. Because, you know, we had no demonstration before that. Yes, for experiment with pigs, but we have no data coming from a human infant. So in this microphotograph coming from the lung histology of that particular baby, published in New England Journal of Medicine, you may see how the lungs are totally deorganized. Alveoli are almost not recognizable. There's a lot of fibrosis, and you may see that the structure is totally different from the structure of a normal lung. Unfortunately, we cannot see that every day, but at least we can see what BPD is after a lung mechanical ventilation from a chest X-rays that I'll show you right now. It's a very damaged lung with a lot of fibrosis and image, even at the radiology, totally different as compared to a normal chest X-rays. So this is why it's frankly better to reduce mechanical ventilation length as soon as possible. And the best option would be to do insure, which means to give surfactant and extubate the baby as soon as possible. Any available mean to reduce duration of mechanical ventilation. For instance, we use very short-acting sedative drugs or drugs not affecting the respiratory centers, and sometimes even using antidotes. As you may see, by using electrical impedance tomography, there is EIT. EIT is a non-invasive technique giving you the possibility to look at the lung volumes in vivo. CPAP is a quite open and nice lung that will be even more open and even more nicer after surfactant administration. So invasive mechanical ventilation is one of the most important risk factors for BPD, and this has been known for a long time because mechanical ventilation is known to be a pro-inflammatory trigger. So very recent data from this graph shows that the larger the duration of mechanical ventilation, the worse will be the respiratory outcome. So BPD babies also have lifelong consequences because they may may be even in need of PICU admission, and they are a higher risk of death. So if we look more long-term, BPD may also impact on neurodevelopmental impairment, requiring educational and social support for these babies. So this is why current guidelines strongly recommend to avoid as much as possible mechanical ventilation. So now, let's talk about something very interesting and very important for me. So the regulation of surfactant catabolism. So, as you may recall from the very first images, there is not just production, but also catabolism. And so these two processes are meant to be considered like some sort of balance. You may have a normal situation, like me, hopefully, right now, with a normal production and a normal surfactant catabolism. This is supposed to achieve a very low alveolar surface tension, usually less than 5 millinewton per meter, which means normal alveoli very well opened. Then you may have three pathological situations. First one, when you have a normal surfactant one, which is really the worst one, sometimes happening in some preterm babies, having both low surfactant production and higher surfactant catabolism. So you can understand, if you think at a more lung level, that when you have lung level, you may have two situations. Either the balance, so a normal lung with a pretty high functional residual capacity, or either a situation, unfortunately, with some sort of the three surfactant injury conditions when you have a low functional residual capacity. So functional residual capacity is the amount of volume of air remaining into the lung by the end of a respiratory cycle. And so it's giving you an idea about how much volume you have to do your gas exchange. So it's very important to keep functional residual capacity high, and this is actually happening only when you have lower surface tension in a normal balance situation, with a normal balance between production and surfactant catabolism. So if all this is true when it's pretty complex as a situation, you may want to ask yourself who is the responsible for that situation. There is actually a main responsible for that, which is a small molecule, a small enzyme that is called secretory phospholipase A2. That enzyme is produced by alveolar macrophages, which are these sort of round cells that are right in the middle of the alveolar. And alveolar macrophages are secreting phospholipase A2 out in the alveolar spaces. And it's there that the phospholipase A2 is actually doing its action. So what phospholipase A2 is doing? It's very easy, and you are going to see that from two separate experiments, one in pigs and another in human neonates. So on the left, you have the pig experiment. Somebody injected phospholipase A2 into the pig trachea. And you may see that with increasing concentration of phospholipase A2, you may have increasing surface tension and also increasing percentage of surfactant hydrolysis. So you may see PLA2 is actually destroying surfactant over there. While on the other way around, we did an experiment in human neonates. Clearly, we did not inject any phospholipase into the neonatal trachea, but instead, we did some bronchoalveolar lavages in these neonates. And in the bronchoalveolar lavage fluids, we measured phospholipase A2 activity. On the other way, we measured dynamic compliance. So compliance is something that can be measured with mechanical ventilators, and it gives you an idea about how stiff is the lung. So how stiff is the lung means basically how much FRC, how much functional residual capacity you have, which means how much active surfactant you're going to have over there. So dynamic compliance is a proxy for the amount of active surfactant. So you see there is an inverse correlation between dynamic compliance and the phospholipase A2 activity. So again, even in human neonates, phospholipase A2 is able to destroy surfactant and impacting on dynamic compliance and so on the lung function. So how in details phospholipase A2 is working? That's easy. And you may see in this animation, in these pictures, phospholipase A2 is secreted and is approaching to the surfactant film. Once phospholipase reaching one surfactant phospholipids into its catalytic site, and it's there that is destroying the phospholipids. Once phospholipase A2 has done that, surfactant, unfortunately, will be no more able to lower surface tension and so to exert its main. Now, physiology. Look a little bit. So let me tell you some basic concepts before moving to the actual data. The first concept is we have been able to measure surfactant half-life. So half-life is the time needed to have at least 50% of your phospholipids still there after your normal recycling or catabolism. We have been able to measure that using a small portion of radiolabeled surfactant injected to the babies. It's a lot of studies have been done like that. It's a safe procedure, and I will present you some data about that. A second important point is a clinical index called OI, or oxygenation index. So oxygenation index is really the measure of your clinical severity in terms of oxygenation deficit. It's a very nice calculation, it's very simple formula. let me see here, than multiplying your mean airway pressure, so the help given by the ventilator to the baby, per the FiO2, so the percentage of oxygen given to the baby, divided by the PaO2, so the partial tension of oxygen into your blood. So you see in the numerator you're going to have what you are given to the baby, and on the denominator you're going to have what you are receiving in exchange for your help to him. OI in this sense is very interesting because it's able to describe in a unique figure the clinical severity of the oxygenation, because it's taking into consideration everything, oxygen, pressure, and everything. Usually, therapeutic thresholds for very, very severe cases, like babies are going to be under ECMO or nitric oxide, but now we're going to use OI just to describe the situation of babies getting surfactant. So let's take a look at the data. That's a very nice study from Virgilio Scanielli group comparing babies getting 200 milligrams is much higher than in babies getting the 100 per kilogram. On the other way around, there are other data even more interesting, demonstrating that babies getting only 100 milligrams per kilo are at a double risk of needing a second dose later on. It's around 70% versus 30%. And if you look at the OI, so the clinical severity of these babies, after having received 100 or 200 milligrams per kilo, well, you will see that the OI will be much compared to babies getting 200 milligrams per kilo that are getting a much better oxygenation. So let's enter typical surfactant composition. You know, surfactant is a complex mixture having more or less 90% of phospholipids. And so within this 90%, you may have a lot of different types of phospholipids. The main one is DPPC, dipalmitoyl phosphatidylcholine, which is the main responsible for lowering surface tension. In addition to that 90%, you also have 10% of proteins, in particular surfactant protein B or SPB, which is the protein responsible for surfactant film formation. Able to change lamellar bodies into a film for surfactant to exert its biophysical activity. So as much SPB you have, the quicker and more. It's not only about the amount of surfactant, but also create a film and to keep the alveoli open. To confirm what I said, Olivier Danaive's group made a very nice experiment in vitro, and you may see here the results. There is a very nice inverse correlation between the amount of SPB available in surfactant and the concentration-dependent efficiency of surfactant film formation. It's important to note that not all commercially available surfactants contain the same amount of SPB. For example, as you may see here in this image that is based on calculation for a recommended dose for a 1 kilo baby, you have 200 milligrams of prolactin alpha and 100 milligrams of another surfactant. So you may see that the amount of SPB is much higher for prolactin alpha than for the other surfactant. So even with a smaller volume of prolactin alpha, the amount of SPB is higher than in the other surfactant at the recommended treatment doses. As you may see here with these in vivo data that are coming from a lamb model, using prolactin alpha at the recommended dose of 200 milligrams per kilo, the surfactant distribution is very quick and occurs within 1 as quicker as more effective will be your surfactant film. So it's not only about the amount of surfactant, but it's also about the capacity of your surfactant to create the film and lie open. So going back to surfactant composition, we already talked about DPPC, which is the key phospholipid for important. For example, let me tell you something about deoylate phosphatidylglycerol or DOPG, which is an anion phase tension, but still is very important because it's able to regulate and downgrade the surfactant catabolism. So in the end, the OPG is a kind of helper because it's helping the PPC in exerting its biophysical activity. And to be honest, it's not even the only one, because in the 10% of surfactant protein, there is also surfactant protein A, or SPA, which is able to do the same. Let's have a look more in details, and here there are some data coming from an animal experiment performed a few years ago in the Institut Pasteur in Paris. So here, some alveolar macrophages were cultured and incubated. So clearly you may see that when you incubate alveolar macrophages with SPA and the OPG, the SPLA2 expression is going significantly down. And the same applies in terms of SPLA2 activity as shown by several other papers. So this means that actually SPA and the OPG, although they are present in lower concentration, they are extremely important because they don't play any significant role in the reduction of surface tension, but still they preserve surfactant activity. We have to pay attention of that, and this is strictly related to the dose, because I really want to catch up with another study of mine, analysis, putting together to understand what were the factors impacting on the need for a redosing. If you can see here, if you receive 100 milligrams per kilo surfactant as a first dose, your odds to receive any other doses later on is much higher, with an odds ratio of 7.27. What does that mean? This means an odds to receive repeated dosing 7 times higher as compared to the 200 milligram per kilo dose. But why so? Because when you receive 100 milligram per kilo, you not only receive half of the DPPC you would have received with the 200 milligram per kilo dose, but also you receive less DOPG. Is that important? Potentially yes, because the OPG is the only available surfactant protector, which means less capability to preserve your surface tension lowering activity. So just to show you how important is the right dose for surfactant, like for any other drug, I want to show you a study of my group that has been recently published in Archives of the. So we analyzed 455 babies born in Parisian areas, both in third and in second level centers. And we finally find out that there was a relationship between the surfactant dose and the gestational age. That means that, unfortunately, babies born at the limited gestational age, so the smallest one, the 24, 25, 27 weekers, are receiving a greater dose as compared to the right 200 milligram per kilo dose. The other way around, the bigger babies are undertreated. They are receiving a lower dose, just because usually people don't care about that and they pay the risk to give surfactant that is just into the vial without respecting the correct 200 milligram per kilo dose. And then, if we analyze these babies in respect of the need for redosing later on, you will see that unfortunately only 50% of these babies will receive the correct dose. And those who were undertreated are at a significantly higher other vials to finally get the needed amount of surfactant. The 2015 Cochrane meta-analysis compared porcine surfactant versus modified bovine surfactant, and the results reinforced the superiority of Curasurf as shown in the Sync 2011 meta-analysis. In fact, as you can see from this forest plot, shown in this other plot, modified bovine surfactant also significantly increases the rates of death or oxygen dependence at 36 weeks gestation postmenstrual age. So Cochrane meta-analysis showed us the different impact of using different surfactants in terms of big outcomes like mortality. But even if we look in terms of secondary outcomes like frequency of extubation and duration of mechanical ventilation after surfactant administration, all things that are important for BPD development, babies getting 200 milligram per kilo prolactin alpha are going better than those getting 100 milligram per kilo beractant, and these are groups very recently. guidelines have been published with regards to surfactant replacement therapy for neonatal RDS. So, for example, European guidelines that have been recently updated in 2016, Prolactin alpha is recommended at an initial dose of 300 mg per kilo, as it performs better than 100 mg per kilo prolactin alpha or beractant for treatment of RDS. And this recommendation is reported as A1, which means high quality of evidence. On the other side of the ocean, the American Academy of Pediatrics guidelines state no recommended dose, but instead they say that the dose should be designed according to pharmacokinetic data, which means, again, but anyway, in the US, prolactin alpha is only licensed for an initial dose of 300 mg per kilo for the treatment of neonatal RDS. So I hope you liked our overview. Only the tip of the iceberg, because surfactant physiopathology is very much complex, and even right now there are many people investigating it and trying to improve. So as you heard, we talked about lung physiology, we talked about surfactant physiopathology, and also the evidences for the treatment of RDS. But in the end, it's all about babies. So how all this can help me in my day-to-day practice? Well, let me give you a brief insight about our daily activity, trying to save as many babies as possible for sometimes the worst clinical scenario every single day.